There is an experiment you can run in a laboratory today, where the outcome of an event appears to depend on a decision made after the event has already ended. A particle moves through a device. It lands on a detection screen. Its position is recorded. Only then do you decide whether to check which path it took. And depending on that choice, made after the particle has already arrived, the pattern of where thousands of those particles landed changes retroactively. Not in the future, in the data that was already recorded. This is not a theoretical curiosity or a misread of ambiguous numbers. It has been repeated in multiple independent laboratories using different particle types and different experimental configurations. The result is always the same. A decision made in your present is connected to a physical outcome that occurred in the past, and our best understanding of causality has no satisfying explanation for how that is possible. Before we dive deeper, if this kind of content genuinely interests you, consider subscribing, because what you're about to see only gets more surprising from here. Now, let's continue. What makes this particularly uncomfortable is that quantum mechanics is not a fringe theory. It is one of the most precisely verified frameworks in the entire history of science. The semiconductors in every computer, the lasers in every fiber optic cable, the magnetic resonance scanners used in hospitals, the GPS satellites that position your phone to within a few meters, none of these would function if quantum mechanics were even slightly wrong. Its predictions have been confirmed to more decimal places than almost any other theory physics has ever produced. And yet, when you ask what quantum mechanics actually means, what is really happening beneath the mathematics, the physicists who built the theory and have spent their careers studying it cannot agree. Not on peripheral details, on everything that matters. Whether particles have definite properties before you measure them. Whether the universe splits into parallel versions every time a quantum event occurs. Whether the act of observation plays a fundamental role in determining which outcome becomes real. Whether the past is fully fixed or whether it is still being shaped by what happens now. These are not questions from the fringes of physics. They are the central unresolved problems of the field. And they have been unresolved for nearly 100 years. Understanding why requires going back to the beginning, not to philosophy, but to experiment. In the world of everyday experience, objects behave according to patterns that feel natural. A ball thrown through the air follows a predictable arc. A light switch produces light. If you want to know where something is, you look at it, and the act of looking does not change the thing you are examining. The universe feels mechanical, deterministic, and separate from the people observing it. This intuition was formalized over centuries of physics, first by Newton and later extended by Einstein. Every event had a prior cause. Every state of the universe followed from the state that preceded it. Given perfect knowledge of the present, you could, in principle, calculate the future in any direction. You could predict where a cannonball would land, where a planet would be in 1,000 years, how a comet would arc through the gravitational field of the solar system. The mathematics was deterministic, the universe felt solid, and the separation between observer and observed was taken for granted. Then physicists started examining very small things, and the entire framework broke down. Not slightly. Not in a way that could be repaired with better instruments or more sophisticated equations. The rules that governed balls, planets, and light switches simply did not apply to electrons, photons, and atoms. What replaced those rules was a theory that worked with extraordinary precision, but made almost no intuitive sense as a description of what was actually happening. The central feature of quantum mechanics is this: a particle does not have a definite position, speed, or state until you measure it. Before measurement, it is described by something called a wave function, a mathematical object that encodes all the possible states the particle could occupy, each with a certain probability. Crucially, the particle is not secretly in one of those states while you simply remain ignorant of which one. It genuinely occupies all of them simultaneously, in a condition called superposition. When you measure the particle, the wave function collapses. One outcome emerges from the range of possibilities. The measurement has not uncovered a pre-existing fact. It has, in some meaningful sense, created the fact that is already difficult to absorb. But the difficulty compounds the deeper you push, because the equation that describes how the wave function evolves over time, the Schrödinger equation, contains no mechanism for this collapse. It simply describes a wave function spreading through all its possible states, evolving smoothly and continuously. There is no point in the mathematics where the particle suddenly chooses. There is no built-in rule for when probabilities convert to a single, definite outcome. The collapse is added to the theory almost as an afterthought, because without it, the equations cannot connect to the things you actually measure in a laboratory. This gap, the absence of a physical mechanism for collapse, is called the measurement problem, and it sits at the center of every paradox, every debate, and every unresolved question in quantum physics. The measurement problem is not the result of insufficient thought. It is a problem where every serious proposed solution generates new difficulties, at least as severe as the ones it resolves. And the reason it cannot simply be shrugged off as an abstract philosophical nuisance is that its consequences appear in real experiments, producing real data that real instruments record. Richard Feynman, arguably the most computationally brilliant physicist of the 20th century, stated plainly that nobody understands quantum mechanics, not as a personal confession but as a summary of the collective condition of the field. Niels Bohr, who contributed more than almost anyone to building quantum theory, said that anyone who is not shocked by it has not understood it. Erwin Schrödinger, whose equation is the mathematical backbone of the entire framework, said late in his life that he regretted ever having anything to do with it. Albert Einstein spent the final decades of his life insisting the theory must be incomplete because its implications violated every instinct he had about how a coherent universe should work. These were not people confused by the mathematics. They had constructed the mathematics, and they still could not tell you what was really happening. To understand the specific experiments that reveal this confusion at its sharpest, start with the one that opened this discussion. The delayed choice quantum eraser is a refined version of the double-slit experiment, which is itself one of the most important experiments in the history of science. In the double-slit setup, particles are fired one at a time through a barrier containing two narrow openings. When no one checks which slit each particle passes through, the particles build up an interference pattern on the screen behind the barrier, the same overlapping wave pattern you would see if you dropped two stones into a still pond. This indicates that each individual particle traveled through both slits simultaneously, interfering with itself as a wave. The particle behaved not like a compact object, but like a spreading field of probability that passed through both openings at once. When you add a detector to check which slit the particle actually went through, the interference pattern disappears. The particle now behaves like a solid object passing through one slit only. The pattern shifts from wave-like to particle-like. The only thing that changed was whether information about the path was available. The act of knowing changes the physical outcome. The delayed choice quantum eraser takes this further. In this version, the particle passes through the system and registers its position on the screen before any decision is made about whether to record which path it took. The particle has already arrived. Its position has already been measured. Only after all of that do you choose whether to erase or preserve the path information. When you preserve the path information, the particles analyzed after the fact show no interference pattern. When you erase the path information after the particles have already hit the screen, the data shows an interference pattern. A decision made after the event determines which pattern the event produced. To be precise about what this does and does not mean, you cannot use this effect to send information backward through time. The interference pattern only becomes visible when you sort the recorded data into subgroups based on what you later decided to do with the path information. Any individual particle's detection position tells you nothing useful on its own. The effect only emerges statistically across many particles, sorted retroactively. So classical causality is not violated in a way that permits backward communication. But the pattern itself, the fact that your after-the-fact decision about information determines whether interference occurred, remains genuinely unexplained. Some physicists interpret this by arguing that particles have no definite history until all relevant information is in place. Others suggest that time itself is more flexible at the quantum scale than our experience implies. There is no consensus interpretation that satisfies everyone. What is not in dispute is that the result is real, reproducible, and points at something fundamental about the relationship between time, information, and physical outcomes. There is an experiment you can run in a laboratory today where the outcome of an event appears to depend on a decision made after the event has already ended. A particle moves through a device. It lands on a detection screen. Its position is recorded. Only then do you decide whether to check which path it took, and depending on that choice, made after the particle has already arrived. The pattern of where thousands of those particles landed changes retroactively, not in the future, in the data that was already recorded. This is not a theoretical curiosity or a misread of ambiguous numbers. It has been repeated in multiple independent laboratories using different particle types and different experimental configurations. The result is always the same. A decision made in your present is connected to a physical outcome that occurred in the past, and our best understanding of causality has no satisfying explanation for how that is possible. What makes this particularly uncomfortable is that quantum mechanics is not a fringe theory. It is one of the most precisely verified frameworks in the entire history of science. The semiconductors in every computer, the lasers in every fiber optic cable, the magnetic resonance scanners used in hospitals, the GPS satellites that position your phone to within a few meters, none of these would function if quantum mechanics were even slightly wrong. Its predictions have been confirmed to more decimal places than almost any other theory physics has ever produced. And yet, when you ask what quantum mechanics actually means, what is really happening beneath the mathematics, the physicists who built the theory and have spent their careers studying it cannot agree. Not on peripheral details, on everything that matters. Whether particles have definite properties before you measure them. Whether the universe splits into parallel versions every time a quantum event occurs. Whether the act of observation plays a fundamental role in determining which outcome becomes real. Whether the past is fully fixed or whether it is still being shaped by what happens now. These are not questions from the fringes of physics. They are the central unresolved problems of the field. And they have been unresolved for nearly 100 years. Understanding why requires going back to the beginning, not to philosophy, but to experiment. In the world of everyday experience, objects behave according to patterns that feel natural. A ball thrown through the air follows a predictable arc. A light switch produces light. If you want to know where something is, you look at it, and the act of looking does not change the thing you are examining. The universe feels mechanical, deterministic, and separate from the people observing it. This intuition was formalized over centuries of physics, first by Newton and later extended by Einstein. Every event had a prior cause. Every state of the universe followed from the state that preceded it. Given perfect knowledge of the present, you could in principle calculate the future in any direction. You could predict where a cannonball would land, where a planet would be in 1,000 years, how a comet would arc through the gravitational field of the solar system. The mathematics was deterministic, the universe felt solid, and the separation between observer and observed was taken for granted. Then physicists started examining very small things, and the entire framework broke down. Not slightly, not in a way that could be repaired with better instruments or more sophisticated equations. The rules that governed balls, planets, and light switches simply did not apply to electrons, photons, and atoms. What replaced those rules was a theory that worked with extraordinary precision, but made almost no intuitive sense as a description of what was actually happening. The central feature of quantum mechanics is this: a particle does not have a definite position, speed, or state until you measure it. Before measurement, it is described by something called a wave function, a mathematical object that encodes all the possible states the particle could occupy, each with a certain probability. Crucially, the particle is not secretly in one of those states, while you simply remain ignorant of which one. It genuinely occupies all of them simultaneously, in a condition called superposition. When you measure the particle, the wave function collapses. One outcome emerges from the range of possibilities. The measurement has not uncovered a pre-existing fact. It has, in some meaningful sense, created the fact that is already difficult to absorb, but the difficulty compounds the deeper you push, because the equation that describes how the wave function evolves over time, the Schrödinger equation, contains no mechanism for this collapse. It simply describes a wave function spreading through all its possible states, evolving smoothly and continuously. There is no point in the mathematics where the particle suddenly chooses. There is no built-in rule for when probabilities convert to a single definite outcome. The collapse is added to the theory almost as an afterthought, because without it, the equations cannot connect to the things you actually measure in a laboratory. This gap, the absence of a physical mechanism for collapse, is called the measurement problem, and it sits at the center of every paradox, every debate, and every unresolved question in quantum physics. The measurement problem is not the result of insufficient thought. It is a problem where every serious proposed solution generates new difficulties at least as severe as the ones it resolves, and the reason it cannot simply be shrugged off as an abstract philosophical nuisance is that its consequences appear in real experiments, producing real data that real instruments record. Richard Feynman, arguably the most computationally brilliant physicist of the 20th century, stated plainly that nobody understands quantum mechanics, not as a personal confession, but as a summary of the collective condition of the field. Niels Bohr, who contributed more than almost anyone to building quantum theory, said that anyone who is not shocked by it has not understood it. Erwin Schrödinger, whose equation is the mathematical backbone of the entire framework, said late in his life that he regretted ever having anything to do with it. Albert Einstein spent the final decades of his life insisting the theory must be incomplete, because its implications violated every instinct he had about how a coherent universe should work. These were not people confused by the mathematics. They had constructed the mathematics, and they still could not tell you what was really happening. To understand the specific experiments that reveal this confusion at its sharpest, start with the one that opened this discussion. The delayed choice quantum eraser is a refined version of the double-slit experiment, which is itself one of the most important experiments in the history of science. In the double-slit setup, particles are fired one at a time through a barrier containing two narrow openings. When no one checks which slit each particle passes through, the particles build up an interference pattern on the screen behind the barrier, the same overlapping wave pattern you would see if you dropped two stones into a still pond. This indicates that each individual particle traveled through both slits simultaneously, interfering with itself as a wave. The particle behaved not like a compact object, but like a spreading field of probability that passed through both openings at once. When you add a detector to check which slit the particle actually went through, the interference pattern disappears. The particle now behaves like a solid object passing through one slit only. The pattern shifts from wave-like to particle-like. The only thing that changed was whether information about the path was available. The act of knowing changes the physical outcome. The delayed choice quantum eraser takes this further. In this version, the particle passes through the system and registers its position on the screen before any decision is made about whether to record which path it took. The particle has already arrived. Its position has already been measured. Only after all of that do you choose whether to erase or preserve the path information. When you preserve the path information, the particles analyzed after the fact show no interference pattern. When you erase the path information after the particles have already hit the screen, the data shows an interference pattern. A decision made after the event determines which pattern the event produced. To be precise about what this does and does not mean, you cannot use this effect to send information backward through time. The interference pattern only becomes visible when you sort the recorded data into subgroups based on what you later decided to do with the path information. Any individual particle's detection position tells you nothing useful on its own. The effect only emerges statistically across many particles, sorted retroactively. So classical causality is not violated in a way that permits backward communication. But the pattern itself, the fact that your after-the-fact decision about information determines whether interference occurred, remains genuinely unexplained. Some physicists interpret this by arguing that particles have no definite history until all relevant information is in place. Others suggest that time itself is more flexible at the quantum scale than our experience implies. There is no consensus interpretation that satisfies everyone. What is not in dispute is that the result is real, reproducible, and points at something fundamental about the relationship between time, information, and physical outcomes. Beginning with pioneering work by John Clauser in the early 1970s, refined dramatically by Alain Aspect in the early 1980s, and confirmed repeatedly by increasingly precise measurements over the following decades, experiments showed consistently that quantum mechanics was right. The Bell inequalities were violated. The universe produces correlations too strong to fit inside any classical picture. Alain Aspect, John Clauser, and Anton Zeilinger received the Nobel Prize in Physics in 2022 specifically for this experimental work. What Bell inequality violations tell us is not just that quantum mechanics is accurate. They tell us that the universe is fundamentally different from any classical picture. The world is either not local, meaning influences can propagate faster than light in some sense, or not realistic, meaning particles do not have definite properties before measurement, or both. Neither option fits comfortably into everyday intuition, and the experiments leave no escape route. Now consider what happens when you try to separate not two objects, but a single object from its own properties. There is an experiment called the quantum Cheshire cat, named after the character in Lewis Carroll's story, who gradually disappears until only the grin remains floating in midair. The name fits with uncomfortable precision because the experiment appears to demonstrate exactly that, a particle and one of its defining properties traveling through an apparatus by separate routes. The setup uses neutrons and a device called an interferometer, which splits a beam of particles into two possible paths and then recombines them. Quantum mechanics places the neutron in a superposition of both paths simultaneously. What is unusual is what emerges when you design the measurement scheme carefully enough to independently probe where the neutron's position is detected, and where its spin, an intrinsic quantum property, is detected, using a technique called weak measurement, which extracts partial statistical information from a quantum system without forcing it into a definite state. The experiment accumulates results across many runs. The picture that emerges is this. The neutron's position appears in one arm of the interferometer. The neutron's spin appears in the other arm. In classical physics, this is incoherent. A spinning top does not leave its spin behind when it crosses a room. An object's properties go where the object goes. There is no mechanism by which one property could depart from a whole and travel independently. But in the quantum Cheshire cat experiment, that appears to be exactly what is recorded. Some physicists interpret this as revealing that quantum objects are not objects in any classical sense. They are not discrete entities carrying a bundle of properties through space. They are more like nodes of interconnected probabilities, and those probabilities can be arranged in configurations that separate what we would ordinarily consider inseparable aspects of a single thing. Others interpret the weak measurement results more cautiously, arguing that the apparent separation is a mathematical artifact of how the measurement scheme functions, not evidence of literal spatial separation between particle and property. The philosophical debate is genuine. What is not in dispute is that the experimental results are consistent with the quantum Cheshire cat effect. Whatever interpretation you prefer, the data is real. If a particle's properties can be detected in separate regions of space, then questions about what it means to be a unified object become suddenly complicated. Is a neutron a discrete thing? Or is it a collection of quantum properties that happen to be correlated under ordinary circumstances but can, under specific conditions, come apart? These questions lead naturally to one of the most philosophically provocative thought experiments in physics: quantum suicide. The thought experiment begins with the many worlds interpretation, which is one of the most seriously considered responses to the measurement problem. In the many worlds view, the wave function never collapses. Every time a quantum event can produce multiple outcomes, the universe branches. Every outcome occurs, but in separate non-communicating versions of reality. When Schrödinger's cat is placed in its box, the universe divides into a branch where the cat is alive and a branch where it is dead. Both are equally real. Neither version of the cat has any awareness of the other. This interpretation has certain advantages. It removes the need for collapse as a special physical process. It treats the wave function as literally real rather than as a calculating tool. And it reproduces all the same empirical predictions as standard quantum mechanics. It also has certain costs. The most obvious is the enormous proliferation of unobservable parallel universes that it requires. But the quantum suicide thought experiment takes the interpretation seriously and asks what it implies for a conscious observer facing a potentially fatal quantum event. Imagine a device connected to a quantum trigger, a measurement, with a 50% probability of outcome A and a 50% probability of outcome B. If outcome A occurs, nothing happens. If outcome B occurs, a lethal mechanism fires at the person running the experiment. The trigger is genuinely quantum, not merely probabilistic in the classical sense, but fundamentally undetermined by any prior conditions. The person activates the device. In the many worlds view, both outcomes occur. In one branch, outcome A happens and the person survives. In another branch, outcome B happens and the person does not. Here is the crucial point. The observer can only have a continued experience in the branch where they survived. Consciousness, whatever it is and wherever it comes from, can only follow the thread of experience through branches where the observer continues to exist. There is no experience of outcome B from the first-person perspective. There is no moment where the observer perceives their own discontinuation, because perception requires a perceiver, and the perceiver only exists in the branch where survival occurred. From the first-person perspective, regardless of how many times the experiment is repeated, the observer always survives. They always find themselves in the branch where they made it through, no matter how vanishingly improbable that branch becomes as the experiment is iterated. There is always some branch where the observer has survived every trial, and that is the branch their stream of experience must inhabit. This is sometimes called quantum immortality. If many worlds is correct, and if consciousness must follow the thread of experience through branches where the observer continues to exist, then from the inside, no conscious observer can ever reach a terminus. From the outside, observers in other branches see something quite different. Some witness a colleague who survived every trial. Others witness different outcomes in their respective branches. The first-person perspective of the survivor cannot be reconciled with a third-person statistical account, observed from outside. The thought experiment requires no new physics. It is a logical consequence of applying an existing interpretation of quantum mechanics to conscious observers. What it exposes is how little quantum mechanics actually tells us about the relationship between physical processes and first-person experience. The theory handles particles and probabilities with extraordinary precision. It says almost nothing coherent about what it means to be the person running the experiment. Some physicists treat this as evidence that the many worlds interpretation, despite its mathematical elegance, cannot be the complete story. Others argue that quantum immortality is a genuine prediction of the theory and note that it is not falsifiable. Any observer capable of reporting their results is, by definition, a survivor. Still others contend that consciousness is simply not within the scope of quantum mechanics and that the thought experiment misapplies the framework to something it was never designed to address. None of these responses is fully satisfying. The discomfort remains. Then there is the black hole information paradox, which transforms philosophical discomfort into a direct mathematical conflict between two of the most successful theories in the history of physics. Black holes, despite the enormous complexity of what creates them, a collapsing star with a specific mass, rotation rate, composition, and history are described by general relativity as surprisingly simple objects. Once a black hole forms, only three quantities completely characterize it: its mass, its electric charge, and its angular momentum. Everything else about what fell in, the arrangement of atoms, the chemical composition, the pattern of information that distinguished one configuration of matter from another, is, according to general relativity, gone. The black hole does not remember what it consumed. It simply has a mass. This is called the no-hair theorem, and it follows directly from the equations of general relativity. Quantum mechanics says this is impossible. In quantum mechanics, information is conserved as a fundamental principle. When a quantum system evolves, its wave function changes, but the evolution is reversible. If you know the final state of the system and the rules governing its evolution, you can, in principle, reconstruct any earlier state. Information does not disappear. It gets scrambled and spread out across complex correlations, but it is always there. If it were not, the mathematical framework of quantum mechanics, specifically the property called unitarity, which ensures probabilities always sum to 1 and evolution remains invertible, would break down entirely. These two principles sit in direct opposition when applied to black holes. In the 1970s, Stephen Hawking calculated that black holes are not completely black. Quantum effects near the event horizon cause pairs of virtual particles to appear spontaneously. Occasionally, one particle of a pair falls into the black hole while the other escapes outward. Over extraordinarily long timescales, this process gradually drains energy from the black hole through what is now called Hawking radiation. The black hole eventually evaporates and disappears. The problem is that Hawking radiation, as originally calculated, carries no information about what fell in. It is essentially thermal radiation, random, structureless, containing no record of the matter that produced it. If the black hole evaporates completely and the radiation is truly information-free, then everything that fell in is simply gone, permanently, not scrambled or hidden, erased. This is the black hole information paradox, and it has been one of the central unsolved problems in theoretical physics for more than 50 years. Several solutions have been proposed, and each trades one problem for another. One proposal suggests that information is encoded in the Hawking radiation, but in an extraordinarily subtle way, hidden in quantum correlations between photons emitted at different times across the black hole's entire evaporating lifetime. If you had perfect knowledge of all the radiation ever emitted, you could, in principle, reconstruct what fell in. This is sometimes called the Page curve solution, after physicist Don Page, who calculated what an information-preserving evaporation would look like statistically. But demonstrating that the radiation actually encodes this information requires understanding the quantum geometry of the black hole interior at a level of detail that no current theory can provide. Another proposal involves the holographic principle, an idea that emerged from string theory and was developed in detail by physicists including Leonard Susskind and Juan Maldacena. The holographic principle suggests that all the information contained in a three-dimensional region of space can be completely encoded on the two-dimensional boundary of that region. Like a three-dimensional image encoded on a flat holographic film applied to black holes, this implies that information about infalling matter is not lost inside the black hole, but is encoded on the event horizon, the two-dimensional surface at the boundary of the black hole, and is eventually returned to the universe through the Hawking radiation as the horizon shrinks during evaporation. This framework has strong mathematical support in a specific context, a type of spacetime geometry called anti-de Sitter space used in theoretical physics. In that context, a precise mathematical duality exists between a theory of gravity in the interior of the space and a quantum theory without gravity on its boundary, and information is demonstrably conserved. Whether this applies to black holes in the actual universe is considerably less certain. A third proposal, the firewall paradox, was proposed in 2012 by Ahmed Almheri and colleagues. This argument suggests that if information is truly preserved in the Hawking radiation, then the region just outside the event horizon must be dramatically different from what general relativity predicts. General relativity says that an observer falling into a black hole should notice nothing unusual at the horizon. Spacetime there is smooth, and the transition from outside to inside should be unremarkable. But if information is being preserved in the radiation, the firewall argument shows that quantum correlations at the horizon must be structured in a way that creates an intense burst of energy, a wall of high energy, radiation that would destroy anything attempting to cross it. This resolves the information paradox, but violates one of the central principles of general relativity, the equivalence principle, which states that free fall in a gravitational field should be locally indistinguishable from floating in empty space. Every proposed solution to the black hole information paradox preserves something and breaks something else. There is no solution that keeps all the existing principles intact. This is precisely what makes the paradox so significant. It is not a puzzle waiting for a clever mathematical trick. It is a signal that two of our best theories are fundamentally incompatible, and that something big enough to reconcile them is missing. What makes this even more striking is that every one of these paradoxes, the delayed choice eraser, Wigner's friend, quantum pseudo-telepathy, the quantum Cheshire cat, quantum suicide, and the black hole information paradox, converges on the same unresolved core. We do not know what measurement is. That is the measurement problem in its most fundamental form. Quantum mechanics is extraordinarily precise about probabilities before measurement and exactly correct about what you will observe after measurement. It says essentially nothing coherent about what happens during measurement, about what actually triggers the collapse of the wave function, about why you observe one outcome instead of a superposition of all of them, about what even counts as a measurement in the first place. Does a photon detector count as a measurement? Does a bacterium, a human, a sufficiently large classical system, a conscious mind? The theory does not say. The Copenhagen interpretation, historically, the most widely taught version of quantum mechanics, sidesteps the question by simply declining to ask what is happening when no measurement is taking place. The wave function is a tool for calculating what you will observe. Questions about what exists between observations are declared outside the scope of physics. This is pragmatically effective and philosophically unsatisfying in equal measure. The many worlds interpretation answers the question by saying the wave function never collapses. All outcomes occur, the observer branches. But then you need to explain why you experience only one outcome, which pushes the problem into the territory of consciousness and identity, where physics has very few tools. Decoherence. The process by which quantum systems lose their interference properties through interaction with their surrounding environment explains why you never see superpositions at the scale of everyday objects. Once a quantum system interacts with even a few air molecules, the quantum correlations that allow interference are distributed across so many particles that they become practically impossible to observe. The system effectively behaves classically, but decoherence does not explain why only one outcome appears in your experience. It explains why the other outcomes stop being observable, not why they stop being real. Objective collapse theories propose that the collapse is a genuine physical process that happens spontaneously, similar in character to radioactive decay, and that large systems collapse faster than small ones. These theories modify the Schrödinger equation by adding a term that drives superpositions toward definite outcomes at a rate that scales with the number of particles involved. An electron in superposition would take an astronomically long time to collapse spontaneously on its own. A human-scale object in superposition would collapse essentially instantaneously. This is appealing because it restores a single definite reality without requiring observers or consciousness. But no spontaneous collapse has ever been directly detected. Experiments designed to look for its signature in the statistical behavior of large molecules and sensitive detectors are ongoing. The specific mechanism remains unknown, and there is the proposal that consciousness plays a fundamental role, that the wave function collapses when and only when it is observed by a conscious mind. This view is unpopular among most physicists for several reasons. It is vague about what consciousness actually is. It introduces a non-physical entity into an otherwise physical theory, and it seems to invert the usual relationship with consciousness determining physical reality rather than the other way around. But it keeps resurfacing because nobody has found a better explanation for why you always experience a single definite outcome rather than a superposition of all possibilities. The measurement problem is not just a technical issue for specialists to resolve. It is a question about what kind of universe we live in. Is reality a fixed structure that exists independently of observers, fully determined in all its details, waiting to be discovered? Or is reality something that crystallizes in the act of interaction, where properties do not exist independently of the processes that bring them into contact with other systems? These questions are not answered by quantum mechanics. They are forced into view by quantum mechanics, which works with extraordinary precision in every technical application while leaving the fundamental picture of what is actually happening entirely unresolved. 1. Perspective that has attracted serious attention in recent years is relational quantum mechanics, developed by physicist Carlo Rovelli. In Rovelli's framework, quantum states do not have absolute values. They are always defined relative to another system. The state of a particle is not a feature of the particle by itself, but a feature of the relationship between that particle and whatever system is interacting with it. Different systems can have different, mutually consistent descriptions of the same quantum object, because what they are describing is their own relationship to that object, not an absolute fact about the object existing independently. This dissolves some of the tension in the Wigner's friend paradox by acknowledging from the start that the friend and Wigner can have different descriptions without contradiction. They are each describing their own relational state. When they eventually compare notes, the comparison itself is a new interaction that produces a new relational description consistent with both previous ones. Whether this represents genuine progress or simply relocates the mystery depends on what you consider a satisfying scientific explanation. Relational quantum mechanics is mathematically consistent and makes no new empirical predictions. Whether it provides a meaningful account of what is actually happening or simply rephrases the measurement problem in new language is a matter of genuine debate. Related approach comes from quantum information theory, which recasts the fundamental objects of physics not as particles or fields, but as information. In this view, what quantum mechanics is really about is not small objects bouncing through space, but the structure of possible observations and the correlations between them. Particles are not things that carry information. They are patterns in a fabric of information that can be detected in various ways depending on how you interact with them. This perspective underlies much of the work on quantum computing, quantum cryptography, and quantum communication that has driven enormous technological advances over the past 3 decades. It also provides a natural language for discussing the black hole information paradox, where the question becomes not where the physical matter went, but whether the pattern of information that described the infalling matter can be recovered from the outgoing radiation. Some researchers believe information-theoretic approaches point toward the correct path for unifying quantum mechanics and general relativity. The idea that space-time itself might emerge from quantum information, that the geometry of space and time is a consequence of entanglement structure rather than a background in which events play out, is one of the most actively pursued ideas in quantum gravity today. The specific proposal, developed by physicist Mark van Raamsdonk and colleagues, suggests that regions of spacetime that are connected correspond to quantum systems that are entangled. When the entanglement between two quantum systems decreases, the spatial connection between the corresponding regions of spacetime weakens. At zero entanglement, the regions become disconnected, effectively separate universes. The connectivity of spacetime, what we ordinarily think of as the geometry of space, is in this picture a manifestation of quantum entanglement. This is not yet a complete theory. Its domain of applicability is still unclear, and extending the framework to cosmologically realistic spacetimes is an active area of research without resolved answers. But it represents the kind of conceptual shift that might be necessary to genuinely reconcile the paradoxes. If spacetime is not fundamental but derived, then questions about what happens inside black holes, or what information means in the context of Hawking radiation, might have cleaner answers in the underlying quantum description than in the emergent geometric description. 2. Fully appreciate why these paradoxes are so persistent and why the discomfort built into quantum mechanics is not incidental but foundational. It helps to understand how the theory was assembled in the first place. The first crisis came in the late 1800s, when physicists were trying to calculate the spectrum of light emitted by objects heated to glowing temperatures. The classical theory predicted something called the ultraviolet catastrophe. As you move toward shorter and shorter wavelengths of light, the predicted intensity of emission should rise without limit, going to infinity. Obviously, hot objects do not radiate infinite energy. Something was deeply wrong with the classical picture. In 1900, Max Planck found a mathematical formula that matched the actual observed spectrum precisely. But to derive it, he had to make an assumption he himself found bizarre: that energy was emitted not continuously but in discrete chunks, little packets. He called these quanta, from the Latin word for how much. Planck believed this was a mathematical trick, a calculation device that happened to work but did not reflect any real feature of the world. He spent years trying to derive the same result without the discrete packets. He never succeeded. 5 years later, Albert Einstein used Planck's quanta to explain the photoelectric effect, a phenomenon where light hitting a metal surface ejects electrons, but only if the light exceeds a certain frequency, regardless of how intense the light is. If light were a continuous wave, as classical physics assumed, intense light at any frequency should eventually eject electrons, but it did not. Only light above a threshold frequency worked, even at very low intensity. Einstein showed this made sense if light itself traveled in discrete packets, what we now call photons. A single photon of the right frequency carried enough energy to eject an electron. 1 billion photons of the wrong frequency carried no individual packet energetic enough to do anything. This was a radical claim. Maxwell's equations, which describe light as a continuous electromagnetic wave, were among the most successful pieces of physics ever assembled. They predicted radio waves, correctly described optics, and formed the basis of all electrical technology. And now Einstein was saying light was also a particle. Both descriptions were correct, depending on how you interacted with it. That contradiction, light as wave and light as particle simultaneously, turned out to be one of the central puzzles of quantum mechanics, and it still has no satisfying classical resolution. Light exhibits wave behavior, producing interference patterns. It also exhibits particle behavior, arriving in individual discrete packets. So do electrons. So does every other quantum entity. They are not waves in the classical sense and not particles in the classical sense. They are something else entirely, for which ordinary language has no adequate word. Niels Bohr developed a partial model of the atom that used quantum ideas to explain why atoms are stable and why they emit light at specific frequencies rather than continuously. In Bohr's model, electrons can only occupy certain allowed orbits around the nucleus, emitting or absorbing a photon of specific energy when jumping between orbits. This worked remarkably well for hydrogen, the simplest atom. It worked less well for more complex atoms and failed entirely in certain situations requiring a full quantum treatment. Werner Heisenberg, Erwin Schrödinger, Paul Dirac, Max Born, and others then spent the 1920s building the full mathematical framework. Two different mathematical formalisms, Heisenberg's matrix mechanics and Schrödinger's wave mechanics, were developed almost simultaneously. They looked completely different. Paul Dirac and others proved they were mathematically equivalent, two different ways of describing the same physics. The price of this success was conceptual. The theory worked. Nobody could agree on what it was saying about reality. The debates between Bohr and Einstein at the Solvay conferences in the 1920s and 1930s became legendary in the history of science. Einstein kept constructing thought experiments designed to show that quantum mechanics was either incomplete or inconsistent. Bohr kept finding refutations. The exchange sharpened both positions, but resolved nothing. The most famous of these thought experiments was proposed by Einstein, Boris Podolsky, and Nathan Rosen in 1935. Their EPR paper argued that quantum mechanics must be incomplete because it implied that two particles could be correlated in a way that required either faster than light, signaling, or the existence of hidden variables that the theory did not account for. Einstein believed this was a demonstration that something was wrong with the theory. He expected that a more complete framework would eventually explain the correlations without these troubling implications. He was half right. The more complete theory has not been found. But the troubling implications turned out to be real features of the universe rather than signs of a theoretical flaw. The resolution of that debate took nearly 3 decades. In 1964, John Bell proved a theorem drawing a sharp mathematical boundary between what quantum mechanics predicted and what any hidden variable theory could predict. He derived exact inequalities specifying the maximum correlations that any locally realistic theory could produce. Quantum mechanics predicted correlations that exceeded those limits. The experiments confirmed the quantum predictions. The Bell inequalities were violated. The universe is genuinely non-local in a sense that cannot be explained by any classical picture. This result, confirmed repeatedly across increasingly precise experiments and recognized with a Nobel Prize in 2022, is one of the most significant in the history of physics. Not because it shows that quantum mechanics is correct, but because it shows that the universe is structurally different from any picture in which objects have definite properties and interact through local signals. Now consider where all of this leaves us. Quantum mechanics is the most precisely verified theory in the history of science. It underlies everything from the silicon in your devices, to the lasers in your medical diagnostics, to the encryption protocols protecting your communications. Its predictions are correct, to a precision that exceeds virtually any other scientific framework ever constructed. And we do not understand it, not in the sense of failing to calculate its predictions. Those calculations are flawless. In the sense of failing to comprehend what it is describing about physical reality. Every approach to resolving the paradoxes reveals the same pattern. Remove the mystery in one place and it reappears somewhere else, sometimes in a more disturbing form. But this pattern is not unprecedented. In fact, it is precisely what every previous revolution in physics looked like from the inside. Consider what Planck's quantum hypothesis looked like in 1900. It was an unexplained assumption, a mathematical trick that worked but made no physical sense. 50 years later, it was understood as a consequence of a deep theory of matter and light that explained not just the black-body spectrum, but the structure of atoms, the behavior of materials, the nature of chemical bonds, and the mechanism of nuclear reactions. Or consider the situation that preceded special relativity. An inconsistency existed in the equations of electromagnetism when applied to observers moving at different velocities. The inconsistency was precise and mathematical, not vague or philosophical. Einstein resolved it not by patching the equations, but by reconceiving what space and time actually were. In doing so, he revealed that two concepts, previously considered fundamental, the absolute simultaneity of events and the independence of space and time, were both approximations, valid only at low velocities, or Consider the ultraviolet catastrophe itself. Classical physics predicted infinite radiation from heated objects. This was not a small discrepancy. It was a total breakdown of the theory. The resolution required acknowledging that energy was discrete rather than continuous, a change so fundamental that it upended the entire classical picture of what matter and energy were. In each case, what looked like a technical problem turned out to be a signal that something load-bearing in the existing framework was actually scaffolding. And when that scaffolding was removed, what remained was more accurate, more unified, and more elegantly predictive than what had come before. The expectation that something similar will happen again with quantum mechanics is not wishful thinking. It is extrapolation from a pattern that has repeated consistently throughout the history of physics. The pattern does not guarantee that the next step will come soon, or that it will take a particular form, or that the humans who discover it will recognize it immediately when it arrives. But it makes the search worthwhile and the discomfort meaningful. What researchers are looking for in various ways across various programs is a theory that does not simply reproduce quantum mechanics as an input, but derives it as a consequence of deeper principles. A framework that shows why superposition exists and where it gives way to classical behavior. That specifies what measurement is without importing the concept from outside the formalism. That reconciles quantum mechanics and general relativity without patching one or the other, but by revealing both as approximations to something more fundamental. The most striking recent work involves the intersection of quantum information theory and the geometry of spacetime. Researchers have found mathematical connections suggesting that spatial geometry, the connectivity of space itself, might be a consequence of the entanglement structure of quantum states rather than an independent background. If that is correct, the entire picture inherited from classical physics, the container called space, filled with things called particles, is a derived approximation of something far more. Abstract objective collapse experiments are running in laboratories around the world, testing whether the wave function collapses through a genuine physical process that should leave detectable signatures in the statistical behavior of large molecules. No conclusive signal has been found yet, but the experiments continue to improve in precision. Quantum foundations research, once considered a somewhat marginal philosophical pursuit, has become increasingly central to physics. The practical development of quantum computing and quantum communication has made questions about entanglement, information, and the nature of quantum states genuinely important for engineering, not merely for philosophy. And the growing sophistication of experiments has made it possible to test ideas about quantum mechanics that previously seemed beyond experimental reach. We are in a period where the boundary of what can be tested is expanding rapidly, and where concepts that previously seemed purely theoretical are becoming targets of precision measurement. The paradoxes will not disappear. They are features of the theory, built into its structure, but they may become better understood, transformed from sources of confusion into precise guides pointing toward the deeper theory that will eventually contain them. Consider what physics looked like before relativity. Pre-relativistic physicists were confident that absolute time existed and that the speed of light was relative, that it would appear different depending on how fast the observer was moving. Both assumptions were wrong, and their wrongness was diagnosed by attending carefully to a small, persistent inconsistency in Maxwell's equations that most people preferred to overlook. Consider what physics looked like before quantum mechanics. Late 19th century physicists were confident that matter was made of tiny solid particles and that light was a continuous wave. Both were true in limited regimes. Both were insufficient as complete descriptions. The experiments that revealed this, blackbody radiation, the photoelectric effect, atomic spectra, were all anomalies sitting in plain sight, not fitting the existing framework, waiting for someone to take their full implications seriously rather than explaining them away. The quantum paradoxes occupy that same position today. They are sitting in plain sight. They do not fit the existing framework. Some physicists prefer to explain them away by adopting an interpretation that stops asking uncomfortable questions at the right moment. But the data keeps generating them. A century ago, these specific questions could not have been posed in their current sharp form. The mathematical tools did not exist. The experimental technologies did not exist. The conceptual vocabulary did not exist. Now all three are available, and the community of researchers working on quantum foundations is larger, better funded, and more experimentally engaged than at any previous point in history. A century from now, someone may look back at this period the way we look back at pre-quantum physicists confidently predicting infinite radiation from heated objects, with the clear understanding of how much there was still to learn, and with appreciation for how far knowledge can travel when driven by precision, curiosity, and the refusal to be satisfied with answers that do not quite fit. The universe has been running for nearly 14 billion years on whatever rules it actually runs on. We have been trying to figure out those rules for a few centuries. Our current best description is both extraordinarily accurate and demonstrably incomplete. That incompleteness is not an embarrassment. It is a precise diagnosis of where the frontier is located. The quantum paradoxes are not signs of failure. They are the evidence that physics is working correctly, that experiments are precise enough to reveal the edges of the current framework, and that those edges are close enough to the next level of understanding to be probed with careful thought and increasingly sophisticated technology. The paradoxes of observation suggest that the boundary between observer and world might be an approximation, rather than a fundamental division. The paradoxes of entanglement suggest that spatial separation might be less fundamental than it appears. The paradoxes of time suggest that the arrow of time and the asymmetry between past and future might be emergent rather than built into the deepest level of nature. The black hole information paradox suggests that the space-time geometry of general relativity might be an emergent approximation to something more fundamental. Still, all of this is consistent with the history of physics, in which each major theoretical advance revealed that concepts previously considered fundamental were actually derived. Absolute time turned out to be a limiting case of relativistic space-time. The ether turned out to be unnecessary. The deterministic trajectories of classical mechanics turned out to be macroscopic approximations to quantum probability. Each time, something that seemed load-bearing turned out to be scaffolding. When you encounter quantum paradoxes, the correct response is not to dismiss them as too abstract or to accept them as permanent features of a universe beyond comprehension. The correct response is the one that physicists bring to them every day. Take them seriously as clues. Work out their implications carefully. Design experiments that distinguish between competing explanations, and remain genuinely open to the possibility that the concepts you started with may not survive contact with the deeper answer. The universe does not owe us intuitive explanations. It is not designed for comprehension, and yet throughout every previous transformation of physics, it has responded to serious investigation with patterns that yield to mathematical description, patterns that remain coherent, that make predictions, and that open into deeper coherence when pushed far enough. There's no guarantee that this will continue, but it has continued through every previous revolution, and there is no obvious reason why it should stop now. The quantum paradoxes are not the end of the road. They are a marker showing that the road continues through territory we have not yet mapped, toward a destination that will be stranger and more illuminating than anything we currently expect. If you found this exploration useful, consider liking and subscribing so you do not miss what comes next. The questions only get more interesting the further in you go. There is something worth sitting with in the idea that the universe's most successful scientific theory is simultaneously its most philosophically unresolved one. Quantum mechanics is not unclear because it has not been studied enough. It is unclear in ways that become sharper the more carefully you study it. Every attempt to nail down what it means produces new nails sticking out elsewhere. Consider the concept of probability itself, which quantum mechanics uses in a way that differs fundamentally from how probability is used anywhere else in physics. In classical physics, probability is epistemic. It reflects ignorance. When you flip a coin, the outcome is in principle determined by the forces acting on it. The precise angle of your thumb, the air currents in the room, the exact distribution of mass within the coin. The randomness is in your knowledge, not in the coin. If you could measure all the relevant initial conditions with perfect precision, you could in principle predict the outcome with certainty. The probability is a placeholder for missing information. In quantum mechanics, the probability is not like this. Before you measure a particle's spin, it is not that the spin has a definite direction, and you simply do not know which one. The spin genuinely has no definite direction. The probability is not epistemic. It is ontic, a feature of reality itself, not of your knowledge of reality. This is what the Bell inequality violations establish beyond any remaining doubt. If the probability were epistemic, if the particle had a hidden definite state that the quantum formalism simply failed to capture, then the correlations between entangled particles would be bounded by the Bell inequalities. They are not. The universe is genuinely, irreducibly probabilistic at its smallest scales. This has profound implications that extend beyond physics into questions about determinism and free will. If the laws of nature are fundamentally probabilistic at the quantum level, then the classical picture of a deterministic universe in which every future event is fixed by every past event is simply wrong. The future is not determined by the present state of the universe. There are genuine branch points where different outcomes occur with specific probabilities, and nothing in the laws of physics selects which branch is actualized, unless the many worlds interpretation is correct, in which case all branches are actualized, and the question of which one is real simply does not apply. This is not a comfortable place to arrive. Free will debates have historically been conducted in the context of classical determinism, with the question being whether human choices are caused by prior brain states in the same way that planetary orbits are caused by prior gravitational fields. Quantum indeterminacy opens a different question. Even if your choices are not fully determined by prior brain states, is it meaningful to say they are free if they are partly the product of quantum randomness? Randomness is not freedom. A decision influenced by the random decay of a radioactive atom in your neurons is not obviously more meaningful than a decision fully determined by prior causes. These questions do not have resolved answers in physics, philosophy, or neuroscience, but they are made sharper by the quantum picture of the world. And the sharpness is not going to disappear as quantum mechanics matures. Whatever deeper theory eventually replaces or extends quantum mechanics will have to reckon with the fundamental role of probability in nature. Another area where the implications extend beyond ordinary physical intuition is the concept of identity. In classical physics, objects persist through time. The chair you are sitting on is the same chair it was 5 minutes ago in a straightforward sense, the same atoms in roughly the same arrangement, connected by a continuous chain of physical interactions through the intervening period. Identity through time for ordinary objects is unproblematic. At the quantum level, this becomes complicated in multiple directions simultaneously. First, identical quantum particles are not merely similar, they are genuinely indistinguishable in a way that has no classical analog. Two electrons anywhere in the universe are not just the same type of object. They are completely interchangeable in a mathematical sense that has measurable physical consequences. The quantum statistics of systems containing many identical particles, the behavior of gases, the structure of metals, the properties of superconductors, depend crucially on this indistinguishability in ways that would not occur if the particles had individual identities that could in principle be tracked. Second, the identity of a quantum system through time is complicated by superposition. If a particle is in a superposition of being at location A and location B, and you later find it at location A, what was its trajectory between the moment of preparation and the moment of measurement? Was it at A all along? Did it travel from both locations simultaneously? The question does not have a clean answer within the formalism. The particle did not have a definite location during the interval, which means the concept of a persistent object tracing a path through space does not apply in the way it does classically. Third, entanglement complicates the identity of composite systems. When two particles are entangled, they do not have independent states. The pair has a joint state, but neither particle individually has a state of its own. Measuring one instantly determines something about the other regardless of distance. From a certain perspective, the two entangled particles are not two objects. They are one quantum system that happens to be spatially distributed. The individuality of the components is not well defined. These are not merely philosophical quibbles. They are structural features of quantum mechanics that reflect something deep about the nature of physical objects. Classical physics assumed that the universe was made of individual, persistent, clearly identifiable things. Quantum mechanics suggests that individuality and persistence are approximate, descriptions that break down when you examine the world carefully enough. The question of what constitutes a physical object, what makes something a thing rather than a property or a process, is being forced open by quantum mechanics in a way that cannot be resolved by ignoring it. Consider also the Implications for scientific realism. The view that the entities described by successful scientific theories actually exist in a mind-independent way. This is the default assumption of most scientists and most people. Electrons are real. Photons are real. The laws of gravity are real features of the universe. They would exist and operate the same way even if no humans had ever evolved to discover them. Quantum mechanics puts pressure on this view in a specific way. The wave function, the central object of the theory, is not obviously a real physical field in space. It is a mathematical object defined over configuration space, which has many more dimensions than ordinary space. For a system of two particles, the wave function is defined over a 6-dimensional space. For a system of 10 particles, over a 30-dimensional space. For a system of 10 to the 25th power particles, the space has more dimensions than atoms in a galaxy. This mathematical object accurately predicts the probabilities of measurement outcomes. But what it represents physically is unclear. It does not look like a classical field distributed through ordinary 3-dimensional space. It looks like something quite different, defined over an abstract space of possibilities. Whether the wave function is a real physical entity, or a calculational tool that represents our incomplete knowledge, or something else entirely without a classical analog, is not a question with a resolved answer. Different interpretations of quantum mechanics take different positions. Many worlds treats the wave function as completely real and the only fundamental physical entity. Copenhagen treats it as a calculational tool. Relational interpretations treat it as encoding the relational facts between systems. Objective collapse theories treat it as real but modified by a physical process not captured in the standard formalism. The choice between these is not merely philosophical. It has implications for how you design experiments, how you reason about systems you cannot observe directly, and what questions you consider meaningful to ask. The fact that the choice remains genuinely open, that no experiment has yet been designed that definitively distinguishes between interpretations, is itself a remarkable feature of the situation. Experimentalists are working to change this. Searches for the signatures of objective collapse are ongoing. Experiments testing the limits of quantum coherence in increasingly large objects, molecules, biological systems, eventually nanoscale mechanical devices, are probing where quantum superposition gives way to classical behavior and whether that transition is sharp or gradual. These experiments will eventually produce results that some interpretations can accommodate and others cannot. The boundary between quantum and classical, whatever its precise nature, is not beyond experimental reach. It is simply not yet reached. There is also ongoing work on what might be called quantum reconstruction, attempts to derive the rules of quantum mechanics from more fundamental principles, rather than simply accepting them as axioms and asking what they mean. This approach tries to identify what is special about quantum mechanics among all possible probabilistic theories, and why the universe selected this particular set of rules. Researchers have shown that certain axioms about the structure of possible experiments, about how observations can be combined, how probabilities are defined, how systems can be composed, lead essentially uniquely to the mathematical structure of quantum mechanics. This does not resolve the measurement problem, but it provides a different angle of attack. Instead of asking what the wave function represents, ask why the formalism has exactly the structure it has, and whether that structure can be derived from more primitive principles about observation and information. If the rules of quantum mechanics can be derived from such principles, it suggests that the theory is not a description of the physical machinery of the universe in the traditional sense. It is rather a framework for organizing and relating observations, a theory about what can be known rather than about what exists. This reading connects to quantum information theory and to the relational approaches discussed earlier. None of these research directions has yet produced a full resolution. But the field of quantum foundations is more actively experimental and more mathematically sophisticated than at any previous point. The questions are precisely stated. The tools for investigating them are improving, and the accumulation of experimental results over the coming decades will progressively constrain the space of viable answers in ways that no purely theoretical argument can. The scale of what remains unknown is not a reason for despair. It is a measure of how much there is still to discover. The history of physics is a history of questions that seemed permanently mysterious, yielding to careful investigation over timescales of decades. Blackbody radiation resisted explanation for 40 years before Planck's quantum hypothesis opened the door. The nature of radioactive decay was mysterious for decades before nuclear physics provided a complete account. The mechanism of superconductivity took 46 years from its discovery to the first complete theoretical explanation. These were not simple puzzles. They were hard problems that required the development of entirely new conceptual frameworks before they could be solved. The measurement problem, the interpretation of quantum mechanics, the unification of quantum theory with gravity, these are harder problems than any of those. But they are also being worked on by a larger, better-equipped community of scientists than any of those problems ever had. The pace of experimental capability is accelerating. Quantum computers are now operational devices performing specific tasks that classical computers cannot efficiently match, and their development is generating insight into quantum information that feeds directly back into foundational questions. Gravitational wave detectors are probing regimes where both quantum mechanics and general relativity become relevant. Next-generation experiments on quantum coherence in biological and mechanical systems are running across multiple research groups simultaneously. The frontier is active. The questions are real, and the people asking them are working with tools that did not exist a generation ago. When you step back from the specific paradoxes and consider the overall situation, what you find is not confusion, but clarity about exactly what is missing. A century ago, the edges of quantum theory were not even visible. Physicists did not know what questions to ask at the boundary because the boundary had not been reached. Now the boundary is in sharp focus. The experiments that reveal it are precise. The mathematical theorems that characterize it, like Bell's theorem and the various no-go results in quantum foundations, are rigorous. The competing interpretations are clearly formulated, and the work of distinguishing between them experimentally is underway. This is what the leading edge of a scientific revolution looks like from the inside. Not a moment of clarity when the answer arrives, but a progressive sharpening of the question, until the question is precise enough that an answer becomes findable. The quantum paradoxes, the delayed choice eraser, telling us that past and future are not as separate as they seem. The Wigner's friend experiment telling us that observer-independent facts may not exist at the quantum level. The Bell inequality violations telling us that the universe is non-local in a way that no classical picture can capture. The quantum Cheshire cat telling us that a particle and its properties can be spatially separated. The black hole information paradox telling us that quantum mechanics and general relativity cannot both be right as currently formulated are not anomalies waiting to be explained away. They are the data. They are what the universe looks like when you examine it carefully enough. And what the universe looks like, at its smallest and most fundamental scales, is nothing like what common sense would have predicted. It is stranger, more subtle, and more interconnected than the classical picture that served physics so well for centuries. The transition from the classical picture to whatever comes next may be the most conceptually radical step in the history of science. More radical than the Copernican revolution, more radical than Newtonian mechanics, more radical even than special relativity. The reason is that the previous revolutions changed our picture of the large-scale structure of the world, where we are, how things move, how space and time fit together, while leaving the microscopic picture essentially unchanged. Quantum mechanics changes the microscopic picture entirely, and if the resolution of the current paradoxes requires revising our understanding of space, time, information, and observation at the fundamental level, then the next revolution will touch the foundations in a way that no previous revolution did. That is an extraordinary position for physics to be in. It is also, in a specific and verifiable sense, the position that the evidence has placed us. The universe is under no obligation to be comprehensible. The fact that it has responded repeatedly to serious mathematical investigation with patterns that yield to description, and that those descriptions have become progressively more accurate and unified over time, is remarkable. It is not guaranteed to continue, but the track record is compelling. The quantum paradoxes are the universe's current communication to anyone paying close enough attention. They are not saying that physics has failed. They are saying that physics has reached the next level of depth, and that the concepts adequate for everything discovered so far are not quite adequate for what comes next. Figuring out what does come next is the work of the coming decades. The researchers doing that work are operating in an environment richer in experimental data, mathematical tools, and conceptual options than any previous generation. The answer may not arrive soon, but it will arrive, and when it does, it will almost certainly make the quantum paradoxes look, in retrospect, not like permanent mysteries, but like the precisely drawn map of a territory that had not yet been explored. Stay curious. The road continues. There is a specific experiment in quantum mechanics that does not get as much attention as the double slit or the delayed choice eraser, but which deserves more. It is called the quantum Zeno effect, and it reveals something genuinely strange about the relationship between observation and change. In classical physics, watching something does not affect how it evolves. A planet orbits the sun whether or not astronomers are looking at it. A chemical reaction proceeds according to its kinetics, regardless of whether a camera is pointed at it. The universe does not care about your attention. In quantum mechanics, this is not the case. The quantum Zeno effect takes its name from the ancient Greek philosopher Zeno of Elea, who proposed a series of paradoxes about motion. One of his most famous paradoxes argued that an arrow in flight is actually stationary at every individual instant of time, and therefore cannot be moving at all. This seems like sophistry, but the quantum analog has real experimental content. In the quantum version, a system is prepared in some initial state and then allowed to evolve. Quantum systems evolve by spreading their wave function into new configurations. A radioactive nucleus, for example, gradually develops a non-zero probability of having decayed. But if you measure the nucleus frequently enough, checking at every moment whether it has decayed, something unusual happens. The measurement keeps collapsing the wave function back to the undecayed state, because each time you look, the probability of finding it decayed is still very small, and the act of finding it undecayed resets the clock. If you measure often enough, the system never gets far enough from its initial state to change at all. You can, in principle, prevent a radioactive atom from decaying simply by watching it constantly. This is not hypothetical. The quantum Zeno effect has been demonstrated experimentally in multiple systems including beryllium ions, rubidium atoms, and photons in optical cavities. The measurement really does slow and, in extreme cases, halt the evolution of the quantum system. There is a complementary phenomenon called the quantum anti-Zeno effect, where measuring a system at intermediate frequencies actually speeds up its evolution, causing it to change faster than it would if left alone. Both the Zeno and anti-Zeno effects have been confirmed experimentally, and both reveal that the act of measurement is not a passive reading of pre-existing facts but an active intervention that shapes how the system evolves. The quantum Zeno effect raises immediate questions about the role of observation in the physical world. If frequent observation can freeze a quantum system's evolution, then what counts as observation? Does an unattended detector that records data without a human reading it produce the Zeno effect? The experimental evidence suggests yes. The physical interaction between the system and the measuring apparatus is what matters, not whether a human later reads the data. But this pushes the question back. What is it about a physical interaction that constitutes a measurement? The measurement problem again. The Zeno effect also has practical implications for quantum computing. A quantum computer stores information in the quantum states of physical systems, typically the spins of individual atoms or the charge states of superconducting circuits. These states are extraordinarily fragile. Any unintended interaction with the environment constitutes a kind of uncontrolled measurement that collapses the quantum superpositions on which quantum computation depends. Managing this decoherence is one of the central engineering challenges of quantum computing. Current quantum computers operate with error, rates that require quantum error correction, sophisticated schemes that spread quantum information across many physical qubits in ways that allow errors to be detected and corrected without measuring the information directly. This is quantum error correction, and it represents an application of the deep principles of quantum mechanics to practical computation. The fact that it works, that quantum states can be protected long enough to perform computations, is a remarkable demonstration that quantum mechanics is not just a theoretical framework but a set of engineering principles for building new kinds of machines. The progress in quantum computing also provides a new experimental window into the foundations of quantum mechanics. As quantum processors scale up, they approach the regime where quantum systems containing thousands of entangled qubits interact coherently over timescales long enough to perform complex computations. These are the largest quantum systems that have ever been deliberately prepared and controlled. Studying their behavior under various conditions may reveal new phenomena at the boundary between quantum and classical behavior that no previous experiment has been able to probe. There is also ongoing research on what happens to quantum systems at the boundary of extreme gravity, near black holes, near the early universe's dense plasma, and in situations where both quantum effects and strong gravitational fields are simultaneously relevant. The study of the early universe is particularly interesting because the cosmic microwave background radiation, the afterglow of the Big Bang, observed with extraordinary precision by satellite observatories, including the Planck satellite and the Wilkinson microwave. Anisotropy probe carries information about the quantum fluctuations that occurred in the universe's first fraction of a second. Those quantum fluctuations, amplified by the rapid expansion of the early universe in a process called inflation, are believed to be the seeds of all the large-scale structure in the universe today. All the galaxies, galaxy clusters, and cosmic filaments that we can now map across billions of light-years of space. If this picture is correct, then the universe's large-scale structure is a direct consequence of quantum mechanics operating on the smallest possible scales in the earliest possible moment of cosmic history. The pattern of temperature fluctuations in the cosmic microwave background would then be, in a profound sense, a quantum mechanical phenomenon written at cosmic scale. This connection between the very small and the very large, between quantum fluctuations in the early universe and the distribution of matter across billions of light-years today, is one of the most remarkable implications of modern cosmology. It also highlights why a complete theory of quantum gravity, one that correctly describes physics at the intersection of quantum mechanics and general relativity, is not merely theoretically interesting but observationally necessary for understanding the universe's history and structure. The absence of such a theory is not a gap in an otherwise complete picture. It is a gap that sits in the middle of everything. The Big Bang singularity, the initial moment of cosmic history, occurred at conditions where both quantum effects and gravitational effects are simultaneously of dominant importance. Without a theory of quantum gravity, we cannot describe that moment. We cannot say what happened before it, whether the question has meaning, or what initial conditions the universe began with. The first page of cosmic history, in the current state of physics, is blank. Attempts to fill it are among the most ambitious in all of science. String theory proposes that the fundamental constituents of reality are not point particles but tiny vibrating strings of energy, and that different vibrational patterns correspond to different particles. The extra dimensions required by string theory are hypothesized to be compactified to sizes far below anything currently measurable, which is why we do not perceive them. String theory contains a natural candidate for a graviton, the hypothetical particle that mediates the gravitational force, and has produced mathematically rich results, including the ADA-CFT correspondence mentioned earlier. But string theory has not produced specific, testable predictions that distinguish it from competing frameworks in a way that experiments have been able to confirm. This does not mean it is wrong. It means it is incomplete as a physical theory. A framework that makes no unique testable predictions is not yet a scientific theory in the traditional sense. String theorists are aware of this and are working to identify predictions that future experiments could test. The work continues. Loop quantum gravity takes a different approach, attempting to quantize space-time geometry directly rather than starting from particles and strings. In loop quantum gravity, space itself is granular at the smallest scales, not continuous, but composed of discrete units called spin networks. The geometry of space is not a background in which quantum fields live, but is itself a quantum system, subject to uncertainty and superposition. Loop quantum gravity has made some predictions, including a minimum possible length and potential signatures in the polarization of gamma rays from distant cosmic events, which are being searched for by current and upcoming gamma-ray observatories. It faces its own technical challenges in recovering the smooth space-time geometry of general relativity as an approximation in the appropriate limit. This work is ongoing. Both string theory and loop quantum gravity, and several other candidate theories of quantum gravity, face the common challenge that the energy scales at which quantum gravitational effects become dominant, the Planck scale, are approximately 10 to the 19th power times higher than the energies accessible in current particle accelerators. Detecting quantum gravitational effects directly may require technological capabilities far beyond anything currently imaginable. This does not make quantum gravity research pointless. Indirect signatures, theoretical consistency, and mathematical connections to other areas of physics remain productive sources of progress. But it does mean the experimental confrontation between quantum gravity theories may be slower in coming than in previous areas of physics. This is one reason why so much attention has focused on black holes and the early universe as potential observational windows. In those regimes, nature has already performed experiments at extreme energies and densities that no human-built accelerator could reach. The cosmic microwave background, gravitational wave signals from merging black holes, and high-energy gamma rays from astrophysical sources all carry information about physics at energy scales and densities inaccessible to laboratory experiments. Decoding that information, connecting it to theoretical predictions, and using it to constrain the space of viable theories of quantum gravity is one of the most active frontiers in contemporary physics. The detection of gravitational waves by the LIGO observatories, beginning in 2015, opened an entirely new window on the universe. Gravitational waves are ripples in the fabric of space-time itself, produced by the most violent events in the universe, merging black holes and neutron stars. The signals detected by LIGO are exquisitely small. The detectors measure changes in length smaller than 1,000th of the diameter of an atomic nucleus across a 4-kilometer baseline. That any human instrument can detect such a thing is itself a testimony to the precision of modern physics. The waveforms of gravitational wave signals carry information about the sources that produce them, the masses, spins, and orbital dynamics of merging compact objects. Comparing those waveforms to predictions from general relativity has provided new tests of Einstein's theory in regimes never previously accessible. So far, general relativity has passed every test, but the mergers of black holes and neutron stars also produce conditions in their final moments where quantum effects and extreme gravity occur together. And understanding those conditions in full requires the theory of quantum gravity that does not yet exist. Neutron star mergers are particularly interesting in this regard. The dense cores of neutron stars represent matter compressed to densities approaching nuclear density across volumes comparable to a small city. The physics of such extreme matter, what state it is in, what forces hold it together, what happens to quantum fields in such conditions, is not fully understood. The gravitational wave signals from neutron star mergers, combined with simultaneous observations in light, X-rays, and gamma rays from the same events, provide information about this extreme matter that no Earth-based laboratory can replicate. The combination of gravitational wave astronomy, traditional electromagnetic astronomy, and particle physics observations from the same astrophysical events, called multi-messenger astronomy, is one of the most exciting developments of the current era of physics. It represents a new form of observation that simply did not exist before 2015, and that is already generating results. This expanding observational capability is the context in which the quantum paradoxes are being investigated. The paradoxes are not being studied in isolation, in philosophers' offices, remote from the world of measurement and experiment. They are being studied in the same scientific environment as gravitational wave detection, quantum computing, quantum error correction, precision measurements of particle physics, and cosmological surveys. The tools and concepts developed in one area cross-fertilize others. The progress, while slower than a general audience might prefer, is real and cumulative. The current situation in physics combines the most precise measurements ever made with the deepest conceptual uncertainties that have ever been clearly articulated. That combination, extraordinary precision alongside fundamental unresolved questions, is not a sign of failure. It is a sign of a science at its most productive, operating at the exact boundary between what is understood and what is not. The quantum world is not refusing to be understood. It is requiring that the understanding come on its own terms, not on the terms that human intuition, evolved for survival on the surfaces of medium-sized planets, would prefer. Developing new intuitions adequate to the quantum world is part of the work. So is developing new mathematics. So is designing new experiments. So is cultivating a tolerance for sitting with genuine uncertainty. not the comfortable uncertainty of not having looked something up, but the deeper uncertainty of having looked as carefully as possible and found that the question does not yet have an answer. That is where physics is now, not lost, but at the edge of what has been mapped. Every measurement adds resolution to the map. Every paradox more sharply delineated is another piece of the territory brought into focus. The destination is not visible yet, but the direction of travel is clear, and the pace of progress, measured in the quality and precision of the questions being asked, has never been faster. The universe is waiting to be understood more deeply than it currently is. That is the best possible situation for science to be in. There is one more paradox that deserves careful attention, one that is less famous than the others, but perhaps the most philosophically vertiginous of all. It is called the problem of the preferred basis, and it strikes at the heart of why quantum mechanics is so difficult to interpret as a picture of reality. In standard linear algebra, the same vector can be decomposed into components in many different ways depending on which set of basis vectors you choose. A vector pointing northeast can be described as a combination of north and east, or as a combination of northeast and northwest, or as a combination of any other pair of directions that span the relevant space. All decompositions are equally valid mathematically. None is privileged. Quantum states are mathematical objects of exactly this type. A state that looks like a superposition of spin up and spin down when described in one basis looks like a definite state in a different basis. There is no basis-independent fact about whether a quantum system is in superposition or in a definite state. Superposition is basis relative, not an intrinsic property of the system. This creates a serious problem for the many worlds interpretation. In many worlds, when a quantum event can produce multiple outcomes, the universe branches. But the branching must occur in some particular basis. The outcomes must be defined relative to some particular choice of decomposition. Why should the universe branch along the spin-up, spin-down axis rather than some other axis? What selects the preferred basis in which branching occurs? The response most many worlds advocates give is decoherence. When a quantum system interacts with a large environment, a macroscopic measuring apparatus, a heat bath, the air molecules in a room, the environmental interaction selects preferred states, called pointer states, that are stable under that interaction. These pointer states are the ones that persist without rapidly becoming entangled with further environmental degrees of freedom. Decoherence dynamically selects the preferred basis through the physics of environmental interaction. This is a genuine and important insight. Decoherence explains why macroscopic superpositions, cats that are simultaneously alive and dead, measuring needles that simultaneously point left and right, are not observed in practice. The interaction with the environment rapidly entangles these macroscopic systems with their surroundings, distributing the quantum coherence across so many degrees of freedom that no experiment we can perform can detect the interference. The system effectively behaves as if it has a definite classical state, even though, strictly speaking, it is part of a vast, entangled whole. But decoherence does not fully resolve the preferred basis problem. It says that certain states are more stable than others under environmental interaction, but it does not say that those states are the ones in which outcomes are actually definite. In the full many worlds picture, all branches continue to exist. Decoherence explains why different branches do not interfere with each other, but not why you find yourself in one branch rather than being spread across all of them. The problem of why you experience a single definite outcome, which is really the measurement problem again, remains. This connects to another unresolved question, the origin of the Born rule, which is the rule for converting quantum amplitudes into probabilities. If a quantum state has amplitude A for outcome 1 and amplitude B for outcome 2, then the probability of observing outcome 1 is the square of A's magnitude, and the probability of observing outcome 2 is the square of B's magnitude. This rule is extraordinarily accurate. It underlies every precise quantum mechanical prediction ever made. But within the many worlds interpretation, it is not obvious where this rule comes from or why it takes this particular form. In classical probability theory, the probability of an event is related to the frequency with which it occurs across many trials. If you flip a fair coin 1,000 times, you expect approximately 500 heads and 500 tails. The probability of 1/2 is connected to the long-run frequency of 1/2. In many worlds, every quantum event produces all outcomes in different branches. The frequency interpretation of probability does not obviously apply because all outcomes occur with certainty in some branch. The probability of observing heads is not the frequency with which heads occurs. It occurs with certainty in half the branches. Recovering the Born rule and explaining why the probability of each outcome equals the square of its amplitude and not something else from many worlds' first principles is a technical challenge that has generated substantial research but no universally accepted solution. Several approaches have been attempted. David Deutsch and David Wallace developed an argument based on decision theory, a rational agent who knows that all outcomes occur but must bet on which one they will experience should, if they are decision theoretically coherent, assign probabilities according to the Born rule. This argument is mathematically sophisticated and controversial. Some find it compelling. Others argue that it is circular or that it relies on assumptions that are not clearly justified in the many worlds framework. Attempts to derive the Born rule from counting branches also run into difficulties. You might think that if there are two possible outcomes, the probability of each should be 1/2 by symmetry. But quantum mechanics assigns probabilities according to the squares of amplitudes, not equal weights to branches. A quantum state with amplitude 2/3 for outcome A and amplitude 1/3 for outcome B. Wait, to be precise. With amplitudes whose squares give probabilities of 2/3 and 1/3 respectively, cannot be split into equal branches that reproduce the correct probabilities through simple counting. The Born rule is, in this sense, one of the most empirically well-confirmed but theoretically least derived rules in all of quantum mechanics. It works, it is precise, and it is not clear from any interpretation of quantum mechanics exactly why it must take the form it does. Quantum reconstruction programs mentioned earlier have made some progress on this front. Researchers have shown that if you require certain reasonable axioms about the structure of probability in quantum theories, about how probabilities combine when systems are composed, about symmetry under transformations, then the Born rule emerges essentially uniquely. But whether these axioms reflect deep physical principles or are themselves in need of deeper justification is still debated. This entire constellation of issues, the preferred basis problem, the origin of the Born rule, the relationship between quantum probability and physical frequency, represents the interpretational core of quantum mechanics. Getting these questions right matters not just for philosophy but for the eventual development of a theory of quantum gravity. Any theory that successfully unifies quantum mechanics and general relativity will need to be interpretable. It will need to tell us what is real, what measurement does, and why probabilities take the form they do. Getting the interpretation wrong at the quantum level means building the unification on an unstable foundation. This is one reason why some of the most technically sophisticated physicists working on quantum gravity take foundational questions seriously and do not dismiss them as purely philosophical. John Wheeler, who made major contributions to both quantum mechanics and general relativity and who coined the term black hole, spent the later decades of his career asking whether information and observation might be fundamental to physical reality in a way that the standard formalism does not capture. His phrase, "it from bit," the idea that the physical world might emerge from an information theoretic substrate, has influenced subsequent thinking about quantum information and quantum gravity more than is often acknowledged. Carlo Rovelli, whose relational interpretation was mentioned earlier, is another example of a physicist who takes foundational questions seriously as part of the same project as technical work on quantum gravity. His loop quantum gravity program and his relational quantum mechanics are not separate pursuits but aspects of a unified attempt to understand what physical reality is at its most fundamental level. The willingness to take these questions seriously, to not simply accept the formalism and move on, is a distinguishing feature of the researchers who have made progress on the deepest problems: the measurement problem, the interpretation of the wave function, the origin of the Born rule, the relationship between quantum and classical, the nature of spacetime at the Planck scale. These are all aspects of the same underlying puzzle. What kind of thing is the physical world? And what is the relationship between that world and the mathematical structures we use to describe it? That question has driven the deepest revolutions in the history of science. Newton's answer, the world is a collection of massive objects interacting through forces across absolute space and time, produced one revolution. Einstein's answers, space-time is unified, curved by matter and energy, and there is no preferred reference frame, produce two more. The quantum mechanical answer, the world is fundamentally probabilistic, not locally realistic, and the act of observation is not separable from the observed, is the fourth, and whatever comes next will likely require an answer of similar depth and scope. What that answer will say about the nature of time, space, information, and observation is not yet known. It may be that time, as usually conceived, does not exist at the fundamental level and emerges from a timeless network of quantum correlations. It may be that space is similarly emergent, a large-scale structure arising from the entanglement pattern of a timeless quantum state. It may be that the division between observer and observed, which seems so fundamental to experience, is an approximation valid only in the classical limit and absent in the deeper description. All of these possibilities are being actively explored. None is established. All are consistent with what we currently know. And the experiments being designed and run right now will, over the next few decades, progressively constrain which of them, or which combination of currently unimagined ideas, is actually true. The quantum paradoxes are not obstacles to understanding. They are invitations. Each one marks a place where the current map of physics has an edge, where the territory extends beyond what has been charted. Treating them as clues rather than anomalies, as prompts for new theory rather than embarrassments to be managed, is the posture that has driven every previous revolution in the field. The next one is coming. We do not know when or who will find it. We do not know what form it will take or which currently cherished assumption it will require us to abandon. What we do know is that the questions are real, the experiments are real, and the universe, whatever it ultimately is waiting to reveal the next layer of what it actually consists of. That is the most exciting possible situation for a science to be in. Consider how far the understanding of quantum mechanics has actually come, even without a resolved interpretation. In 1900, the quantum was an unexplained assumption. By 1926, the wave equation was written. By 1935, the EPR paradox had sharpened the central tension into a precise argument. By 1964, Bell had converted that argument into a mathematical theorem. By 1982, Aspect had tested it experimentally. By 2022, the Nobel Committee recognized the work as one of the most important results in the history of physics. Each step took decades. Each step required new mathematics, new experimental technology, and new conceptual clarity about what exactly was being asked. The progress was not fast by human timescales, but it was real, cumulative, and exact. The question of whether the universe is locally realistic, whether particles have definite properties and influences travel at finite speed, is now answered. The answer is no. That question, which occupied Einstein for the last decades of his life and seemed permanently beyond experimental reach in the 1930s, is now settled. Other questions that currently seem permanently beyond experimental reach may similarly yield within the next few decades. The question of whether objective collapse occurs as a physical process, whether the wave function collapses through a specific physical mechanism at some scale between a photon and a cat, is being tested now with improved precision. The question of whether space-time is emergent from quantum entanglement is being explored through mathematical results connecting the geometry of space-time to the entanglement structure of quantum states in certain models. The question of whether time is fundamental or derived is being approached from multiple directions simultaneously. The fact that these questions are now being asked precisely enough to be tested is itself a form of progress. A century ago, the delayed choice quantum eraser could not have been performed. The concept of quantum information did not exist. The mathematical machinery to even formulate the preferred basis problem had not been developed. The experimental technology to create and maintain entangled systems of hundreds of qubits did not exist. Now all of this exists, and the frontier has been pushed to a point where what remains unknown is strange precisely because it is subtle, not because the tools for examining it are absent. The subtlety is the signal. When a question persists, despite increasingly sophisticated examination, it is either because the question is genuinely deep, pointing at something structural about reality that requires fundamentally new concepts to address, or because something in the framing of the question is confused, leading the investigation in a direction that cannot reach an answer. Both possibilities require the same response. Continue examining the question carefully, remain open to revising the framing, and take the empirical results seriously regardless of whether they fit existing expectations. Quantum mechanics has repeatedly produced results that did not fit existing expectations. Every time, the results turned out to be more fundamental than the expectations. The expectations were the things that needed revision. The same pattern will almost certainly repeat. The question is not whether, the question is when and in which direction the revision will run. The history of physics offers no reliable guide to the timeline. Revolutions come when they come, driven by the accumulation of experimental evidence and conceptual pressure in ways that cannot be predicted in advance. What can be predicted is that the evidence will continue to accumulate, the pressure will continue to build, and at some point, perhaps in 5 years, perhaps in 50, perhaps in longer, the framework will shift. When it does, the quantum paradoxes will look different from the other side. The delayed choice eraser will no longer seem to suggest retrocausality. It will be understood as a consequence of a deeper framework, in which the past and future are related in a way that the current picture of time does not capture. The Wigner's friend paradox will no longer seem to threaten objectivity. It will be understood as revealing something about the nature of observation and its relationship to physical facts that the current picture of the observer-world relationship does not capture. The Bell inequality violations will no longer seem to require non-locality. They will be understood as consequences of something about the structure of quantum correlations that the current picture of space and locality does not capture. This is not speculation about what the future theory will say. It is prediction about what the future theory will do. It will dissolve the paradoxes rather than explaining them away by providing a deeper picture in which the apparent contradictions are seen to arise from approximations in the current framework. That is what every previous revolution in physics did, and there is strong reason to think the pattern will repeat. For now, the paradoxes stand. They are as sharp as a century of work has made them. They point in consistent directions without yet revealing the destination. And the work of following where they point continues in laboratories, in mathematical physics research, in philosophy of physics, and in the ongoing conversation between theoretical prediction and experimental result that constitutes the living practice of science. The quantum world is not a place of mystery in the romantic sense, not a realm of indefinable forces and unfathomable depths. It is a place of precise mathematical description and exacting experimental verification that has revealed, through that very precision, exactly how much we do not yet understand. The understanding will come. The precision of the questions almost guarantees it. In the meantime, the quantum paradoxes offer something rare and valuable: the opportunity to sit with genuine uncertainty about the deepest features of physical reality, not from ignorance but from knowledge, knowing precisely what we know, precisely how far it extends, and precisely where it runs out. That is an intellectually honest and philosophically interesting place to be. The universe has the answers. We are learning to ask the questions. There is something philosophically significant about the timing of where physics currently sits. Humanity developed quantum mechanics in the early 20th century under the pressure of experimental anomalies that the classical framework could not explain. The theory was built to solve specific problems: the blackbody spectrum, the photoelectric effect, atomic stability, and spectral lines. It solved those problems with remarkable precision and then continued to predict new phenomena correctly. Quantum tunneling, the Lamb shift, the anomalous magnetic moment of the electron, the existence of antimatter, to a degree that left no serious doubt about its empirical accuracy. But the theory was always philosophically unfinished. The people who built it knew this. Bohr, Heisenberg, Born, Dirac, Pauli, they all wrestled with the interpretation, and none of them arrived at a resolution that satisfied their peers completely. The standard narrative presented to students in textbooks and lecture courses is a pragmatic one. Use the formalism. Do not worry about what it means, and calculate the answers to experimental questions. This pragmatic stance, sometimes called "shut up and calculate," has been enormously productive. It enabled the development of every quantum technology that now underlies modern civilization, but it left the foundational questions unresolved. And as quantum technologies have matured, Those questions have become practically relevant in ways that the pragmatic stance cannot indefinitely defer. A quantum computer is not just an application of quantum mechanics. It is a device that engineers the quantum states of physical systems to perform computations. Building better quantum computers requires understanding quantum coherence, decoherence, entanglement, and error correction at a level of detail that forces engagement with questions about what quantum states are and how they relate to physical reality. The demands of quantum engineering are pulling quantum physics toward its foundational questions in a way that pure theoretical research alone could not. Engineers working on quantum error correction are essentially implementing practical solutions to aspects of the measurement problem. They need to understand what happens when quantum systems interact with their environments, how information is preserved and lost, and how to design interactions that protect quantum states without prematurely collapsing them. These are applied versions of the most fundamental questions in quantum foundations. This cross-fertilization between quantum technology and quantum foundations represents one of the most interesting developments in contemporary physics. For most of the 20th century, quantum foundations was treated as a philosophical hobby for physicists who could afford to be speculative, tolerated, but not central. The experimental successes of the theory in every practical application seemed to render the foundational questions irrelevant to working scientists. You did not need to know what the wave function meant to build a laser or design a transistor. That is still largely true, but building a fault-tolerant quantum computer capable of solving problems that classical computers cannot efficiently address requires understanding quantum mechanics at a depth that the pragmatic stance does not provide. The foundational questions are becoming engineering questions. The physicists who can navigate between formal quantum theory and its foundational interpretation are increasingly valuable precisely because the two domains are converging in ways that practical applications require. This convergence is likely to continue as quantum technologies scale. Quantum communication networks, which exploit entanglement to transmit information with security guarantees that no eavesdropping can break, are being developed and deployed. Quantum sensors, which use quantum states to measure physical quantities with precision beyond classical limits, are being refined for applications in navigation, medical imaging, and fundamental physics experiments. Quantum simulations, in which controllable quantum systems are engineered to mimic the behavior of other quantum systems that are too complex to simulate classically, are being used to study problems in chemistry, materials science, and condensed matter physics. All of these technologies live at the intersection of applied physics and quantum foundations. They require deep understanding of how quantum systems behave, how they interact with classical systems, how information is encoded in quantum states, and how that information can be extracted without destroying the features that make quantum computation and communication useful. The engineers and physicists developing these technologies are, in a sense, building practical tools for probing the foundations of quantum mechanics in ways that pure theory could never do alone. The results of that probing will feed back into our understanding of the fundamental questions. The quantum paradoxes are not just philosophical puzzles. They are descriptions of phenomena that occur in real physical systems and that are increasingly relevant to the development of technologies that will shape the next generation of computing, communication, and scientific measurement. Understanding them better is not optional for a civilization that is actively building devices that depend on quantum effects at their core. The pragmatic approach, use the formalism, do not ask what it means, was adequate when quantum technologies were limited to lasers and transistors. As those technologies become more sophisticated, they will demand and reward a deeper understanding of what quantum mechanics is actually describing. The quantum paradoxes are, in this sense, not just invitations to philosophical reflection. They are engineering challenges, and the tradition of physics, going back through every revolution in the history of the discipline, is that the deepest engineering challenges eventually demand and produce the deepest theoretical advances. The next advance is coming. The questions are posed, the experiments are running, the tools are being built, and the universe, as it has throughout the history of science, is waiting to reward those who look at it carefully enough, take its responses seriously enough, and remain curious enough to keep asking what it means. That is the state of quantum mechanics today. Not a closed chapter, but an ongoing inquiry at the most fundamental level that physics has ever reached. not a collection of mysteries that resist understanding, but a precisely delineated frontier that marks exactly where understanding ends and the next level begins. The exploration continues,